objects, thoughts, ideas, and concepts including mathematical objects, which will of course be the main focus for us. Possibly more importantly, a set is a way of packaging up objects which share similar properties in a meaningful way. Consider the set of triangles. We can unambiguously state whether something is or isn't in this set. This is in, so is this, but this shape isn't. It's not a triangle. This lack of ambiguity in what is or what isn't in a set is foundational to set theory. We can also make claims about the set and assess, again without ambiguity, whether they're true or false. It's true that an element of the set of triangles has three sides, but it's not true that the sum of the internal angles is 360 degrees. A set containing the numbers 1, 2 and 3 would be written like this, with curly brackets and the elements separated by commas. We can name the set. In this case, if we say A is equal to the set 1, 2 and 3, we can just refer to the set as A, which is much easier than saying the set containing 1, 2 and 3 again and again. To express symbolically that an element belongs to a set, we use this symbol. For example, if A is the set containing 1, 2 and 3, then 1 is in A and 2 is in A, but 4 is not in A. And we use the symbol for in, but with a line through it to denote not in. In most cases, we don't write out all the elements in a set, but we'll write a shorthand description using something called set builder notation. For example, the set of prime numbers could be written as capital P is the set of little p such that little p is prime. Here the little p is a variable which must satisfy some criterion we call the predicate, since its belonging to the set is predicated on this criterion. In this case, the predicate is being a prime number. Also notice we have a shorthand for the phrase such that, which is this vertical line. It's good practice when dealing with sets of numbers to declare explicitly which sets you're starting with. This is done before the such that symbol. For example, p in the natural numbers such that p is less than 5 is a completely different set to r in the real numbers such that r is less than 5. Two sets are equal if they both contain the same elements. If for all little a in capital A, little a is also in B, and for all little b in capital B, little b is also in capital A, then the sets A and B are equal. This definition means that the order of the elements doesn't matter. We only need to show that they share the same elements. So, if A contains 1, 2 and 3, and B contains 2, 3 and 1, we say 1 is in A and it's also in B, 2 is in A and it's also in B, and 3 is in A and it's also in B. We then do the same for all the elements in B, and so we've shown that A is equal to B. It also doesn't matter if the elements are repeated. Like before, as long as every element in one set can be shown to also be in the other, we still have equality. Generally, we just write the elements in a way that's easiest to read, which usually means without repetitions and often in some sensible order. But just to be clear, it makes no difference to the set, just to us as readers. The size, or cardinality of a set, is the number of elements it contains. So if A contains 1, 2 and 3, then the cardinality of A is 3, and we denote the cardinality of a set with two vertical lines. If a set has an infinite number of elements, like the set of prime numbers for example, then it's perfectly fine to write the infinity symbol as the cardinality of the set. A set is a subset of another if all of its elements are also elements of another set. For example, if A is the set containing 2, 4 and 6, and B is the set containing 1, 2, 3, 4, 5 and 6, then since the elements 2, 4 and 6 which are in A are also in B, then A is a subset of B. And we use this symbol to denote A being a subset of B. If B equals a set little b in the natural numbers such that B is even, which of these are subsets of B? A, 4, B, the set containing 10, 100 and 1000, or C, the set containing A such that A is equal to 2k where k is in the natural numbers? Well, 4 is an element of B, but not a subset. It's really easy to get mixed up between elements and subsets, but a clue is that the word subset contains the word set, and subsets are always sets themselves. The set containing 10, 100 and 1000 is a subset of B, because these are all even numbers. The set of A such that A is equal to 2k, where k is in the natural numbers, is actually another way of writing the even numbers, since 2 times any number is even. And so this is equal to B, but all the elements of this set are also in B, so technically it is a subset of B. This highlights a general property about subsets. All sets are subsets of themselves. We can also take this further to give a different definition of set equality. If A is a subset of B and B is a subset of A, then A is equal to B. This is essentially reframing the earlier definition of set equality, that all the elements in one must also be in the other, but in the language of subsets. If A is a subset of B, but A is not equal to B, then we call A a proper subset of B. This of course implies there are elements in B that are not in A, otherwise they'd be equal. In some textbooks, a proper subset is denoted like this, but sometimes the same symbol is used for subsets that might be equal, so you need to infer from context which they mean. Some textbooks use this symbol for proper subsets, which is more explicit about them not being equal. A really nice and intuitive property of subsets is that if A is a subset of B and B is a subset of C, then A is a subset of C. It's pretty simple to prove, but probably best illustrated visually. If all of the elements in A are in B and all of the elements in B are in C, then all of the elements in A are in C. This property shows up a lot in sets of numbers. For example, all odd numbers are integers and all integers are rational, so we can be sure that all odd numbers are rational. The empty set is a set which contains no elements. It's a special set we give its own symbol and it has its own properties. Firstly, the empty set is a subset of any set. Let A be a set. Since the empty set has no elements, all the elements in the empty set must also be in A. Therefore, the empty set is a subset of A. The second property of the empty set is that it's unique. Let empty set 1 and empty set 2 be two empty sets. Since the empty set is a subset of all sets, we already can deduce that empty set 1 is a subset of empty set 2, and empty set 2 is a subset of empty set 1. This is the definition of equality we saw earlier. If empty sets 1 and 2 are equal, then we only really had a single unique empty set to begin with, and so we can drop the subscripts 1 and 2 and just call them the empty set.